Hey everybody, how's it going today? I hope we're doing well, and in this video we're going to solve logistic regression in Python from scratch. It's a very important one because we are going to teach the idea of logistic regression, what it actually is, not too much into the math. You could go into the statistics a lot. We are not going to do that. It's going to be a simple, from a machine learning point of view, understand what it does, understand how to implement that from scratch in Python, and then as well at the very beginning we're going to show how to do it in Scikit-Learn, which is just, import linear regression and actually start using it. And what it does is solves the problem of binary classification. So binary classification is really just a fancy term for binary. To break it down, binary is two, so it's either this or that, or it is either it is something or it is not something. So the one we're going to be looking at is heart disease. You either have heart disease or you do not have heart disease. That's the binary part. And classification is, well, yeah, we're just trying to classify if you do have heart disease or if you do not have heart disease, trying to predict whether that is true given input data. We'll be given features such as, maybe the idea of like cholesterol. Maybe as you increase someone's cholesterol, it's more likely, and we'll really look at that idea of likelihood, it's more likely that someone would have heart disease, and we can use logistic regression to try and solve that problem. And one thing off the bat, I know it might be a little bit confusing how the term is called regression, and so simple linear regression, multiple linear regression, these are ideas, even polynomial regression are terms that are trying to predict when the output variable is continuous. So we're trying to, regression literally means trying to predict a continuous value, which means, a value from -infinity to infinity, like someone's height. Like not that someone's height could be -infinity, but the idea that it's a continuous value. It's not like class A or class B, zebra, dog, green, yellow. These are distinct, classes. But regression is about continuous values. But logistic regression, it kind of has a mix of both of those because it does predict, class A or class B. It's for heart disease, but it's regression in there because actually under the hood, as we'll see, it's actually modeling continuous values, and then it kind of does a transformation to do the more complicated classification idea. So if you didn't understand that, don't worry about that because we're going to go over all of this anyway. That was just the beginning part, so that hopefully that made a little bit of sense. And so now what we're going to do is load up our heart classification, heart disease classification data set, as well as then import Scikit-Learn's way of just doing this logistic regression idea, very quickly. And that's how you would do it if you weren't implementing from scratch. We would just use this. Okay, so the first thing we're going to do is, I know it's a little bit crazy, but I'm just going to copy and paste a bunch of code in here because it's just annoying. So we have some setup to do, and I'll read it out to you. Basically, we make a directory called .kaggle. Is for hidden files, and the exclamation is for not a Python command, but basically telling the operating system just to do something. Okay, so it's saying make a directory called kaggle in the home. This thing means home. Don't worry about it if you don't understand it. It really doesn't matter. We're going to copy kaggle.json. Well, what the heck is that? Well, that's assuming there's a kaggle.json here, and there it is. But if you were to look, you wouldn't see that. So what you would actually have to do is make a Kaggle account, because we're getting a data set from Kaggle. And so basically here, if you go to Kaggle, have an account, you can go to your account setting over here, and you can make a new API token. So that actually would make a file called kaggle.json, and if it's not called kaggle.json, just call it that. You can upload it here, click upload over there to session storage, put it there, and then the rest of this stuff will work. That basically just authenticates you into Kaggle, knowing that you're authorized to see the data set. Okay, so then we can do, we basically change the modifications on that file, and then we download the data set, which happens to be, you do that with -d, and we get the heart failure prediction data set. And then that makes a zip file, or that would place a zip file here called heart failure prediction.zip. We unzip that, and if I run all of this at the same time, we will see it did all of that for me. And it unzipped to get a file called heart.csv, which we can import with pandas in the usual way. Now, I will say at this point that technically, you do not have needed to watch the previous two tutorials or anything else because this is a standalone idea. But I would recommend most likely watching either my previous simple linear regression video or my multiple linear regression video. My recommendation is definitely the simple linear regression video, and then probably the multiple regression one as well, because logistic regression is pretty much just a more complicated regression idea. But if you, and I have those linked down below if you want to take a look at that. But if you don't want to look at those, try and learn this one without it, and we'll see how that goes. But just if you do get confused, make sure you look at that other lesson first. Okay, so we're going to import pandas, actually I'm going to go back to full screen for a second, and I can close Kaggle, I'm not going to need that. So import pandas as PD. This is for dealing with datasets. Heart is equal to pd.read CSV on the file name, not heat, hearts.csv, and we can show that. We'll show the whole file there. There's none there. It must be called heart.csv, and here it is. Okay, so here's our big data set, and I know that I'm probably in the way for a second, so I'm just going to actually close myself down for a brief moment. That did not seem to do it. There I am, I'm gone. Okay, so here's the data set. We have, for each row of the data, we have an age, the sex, so clearly these are people. One row is a person. They have some specific type of chest pain. They have a resting blood pressure or cholesterol, fasting. That's not what I read that wrong, and I bet you read it the same way I did. And some other ideas. And then at the very end, they have whether they have heart disease or not. Okay, so we can use all of these features because there should be some sort of pattern, as we'll see, that maybe as cholesterol increases, the probability of heart disease increases, for example. Okay, so what are we going to do next? We've loaded up our data set, and now let's just do a simple plot picking, let's choose the, where is it? The max heart rate. Okay, so this is basically the max heart rate. And if you want to read about what, more about what these variables actually are on the Kaggle dataset, if you go to that dataset, and I'll include that link in the description as well, they have some nice metadata on descriptions of the columns. Okay, so we are going to just do a simple plotly graph. Okay, I've been using matplotlib up to this point, and we're going to be needing some more complicated graphs. So for that, I always do, and if you have another visualization library that you prefer, then, you know, go ahead if you want. I like Plotly, and we're going to import plotly.express as px and do a scatter plot. So very similar to matplotlib scatter plot, but this is px. px.scatter, we can actually pass the first item as the data frame itself. That's what we called this pandas data frame here, heart. And we can pass heart and set the x-axis equal to just a column name, maxhr. So that's saying the x-axis is going to be these values. We'll set the y-axis. Y is equal to heart disease. And then I'll also set, I'll just show you what that does for now. And here you go. Okay, here's our data set. And I'm going to zoom out. Oh, I forgot to show myself back again. I know you missed me. Here I am. Okay, so I actually am going to also add in the color, and it's American, so there's no U. I'm used to writing U's. Color is equal to heart disease as well. Okay, so technically you don't need that information because the color is the same as the y-axis, but you'll see what it does here is that it's going to color these ones yellow. The one class is basically the one here. These are all of the ones. We have heart disease equals 1, and it labels that for us. And these are all the one with heart disease equals 0. And here on the x-axis, we have the max heart rate. So we'll see this little bit of pattern, and actually I'm going to close myself down again for a second so you can definitely see it, is that essentially, you see how it's basically like the same line over, but kind of shifted to the left on the top here? And that's because essentially the probability of having heart disease seems to be higher with a lower max heart rate here. Okay, the relationship might be more complicated than that, but as we can see here, there's all these points here with a low max heart rate. But most of the ones with a low max heart rate, there's some exceptions, but most of them actually happen to have heart disease. And these ones, you know, there's a couple, but for the most part, it seems like it's shifted over to the left here. And so it happens at the end here as well. We kind of see there's not many people after this point that happen to have heart disease. There's one example, but for the most part, the people that are past this point here, they seem to mostly have not have heart disease. Okay, so there's this type of pattern, and we can use this and other ones to our advantage. Now, firstly, I'm going to bring myself back. I'll remember that, as well as we're going to do from Scikit-Learn. So from sklearn linear model, it's technically a linear model, it's kind of weird, import logistic regression. Okay, so what we're doing now is Scikit-Learns. We're not implementing from scratch. I'm just showing you how you would do this so you understand what's going on. And yeah, we're going to do this with, we'll get xtrain, and this is a little bit of crazy code, and don't worry about this too much, although I'll explain each piece. Xtrain is equal to heart sub max heart rate, and then dot to NumPy, so converting that to NumPy. And if this is one column, so this is just one flat column here, it's going to be a vector of, and a vector is just a bunch of pieces of information in order. So we have, what is it, 918. So 918 values here. And we can do dot reshape because it's only going to be the shape is just going to be 918 comma. We want that to be the shape of, it'll be 918. And actually, in case that happens to change, I'm going to grab the length of the heart sub age, sub max heart rate. It should actually be the same, but that's fine. Just give it that shape with the length of that and 1. Okay, and just to make sure that that's right, we have xtrain.shape is 918 by 1. Okay, so this is generally how we feed into scikit-learn models, is the shape of a NumPy array with the x, we call it xtrain, like a matrix basically, a table, rows and columns, but without column names. And so 918 by 1, we just have one input variable, so that's why it's that shape. Then we have ytrain, and I'll output its shape even though it doesn't exist yet. Ytrain is our output. Ytrain is equal to heart sub heart disease, and we'll change that to NumPy as well. Okay, so I'll just output, actually I'll just show you here both of them, xtrain.shape and ytrain.shape. Is that here's our inputs and here's our outputs. So we're telling the model that, hey, each time here's the max heart rate, here's the associated value, or here's if they have heart disease or not. Here's the max heart rate, here's if they have heart disease or not, and so on. We're going to train the model to see what happens. So we will do, I'll just do it in another cell. We'll do a logistic regression is equal to logistic regression, bracket, dot fit with xtrain, ytrain. So we train the model, and then we'll do lr dot predict with xtrain to get the logistic regression's predictions. Okay, so here we should have 918 of these values, and so they're all either 0 or 1. 0 meaning they don't have heart disease, 1 meaning they do. And so lr.predict, the shape is 918 comma. Okay, so that's for all of these values here. We now have an associated prediction according to this logistic regression model of whether they do or not. We also have, which is actually going to be not a lot more useful to us necessarily, but very useful when we're going to come to actually implementing this idea. We can do what lr.predict proba, short for probabilities. If we give that xtrain, then here it's this NumPy array where these values are always going to sum to 1, okay? Because that's the proper probability distribution. This part, this is the probability that the model thinks for, well, since this is the first row here, for that first row of information here, which is just for the first person's max heart rate, it thinks that the probability that they have this is basically, this first column is for the 0 class, which is not heart disease. This second column here is for heart disease. So this is the probability that the first person has or does not have heart disease according to our model. This is the probability that the model thinks the first person does have heart disease. This is the probability that the first person or second person does not have heart disease, and this is the probability that the second person does have heart disease. Okay, sorry for stumbling a bit there. It was just a lot to say. I think you get the idea. Sorry for confusing you even more probably. But here's the shape here. It's 918 rows by 2 columns. And so what we can do is if we have, and actually I'm going to do a little bit of just weird stuff here with copying, but that's okay. From copy, import deep copy, we're going to actually copy just the data frame where we get the 2 columns, max HR and heart disease. Okay, so those are our inputs and our outputs. So we're going to copy that. Whoa, I wrote that really weird. Sorry, that was probably very confusing. What I meant to say is from copy, import deep copy, and then we actually set this thing called predictions data frame. And you might remember this from the first and second video if you saw it. Predictions df is equal to the deep copy of what I was just writing. Sorry about that. And so what that is, predictions df here, which is not really any predictions yet, but we're going to add an associated prediction in here so that we see with this input and what the observed heart disease, whether it was or not, what our probability was. So we can add, I'll just keep that there for now. We have predictions df sub. We will call this just probability of heart disease. So I'll just do probability for short actually. Df, so probability is equal to the lr dot predict proba. Okay, the same thing as above with, we could probably just pass it x train as we did before. And then what we could do is run that, and we will see that we have an error. Wrong number of items passed 2. Placement implies 1. Sorry about that. So basically, yeah, I was trying to pass in 2 values here. What I wanted to say is only the probabilities on all the rows and then the second column here. That's how you do that. And so I also had another pair of round brackets here, which I didn't like. And so now here, the probability is right here. Okay. So we will also add in one more column, which is the same thing, except our predictions for whether we actually think they have heart disease or not, which I can actually show you a better way, at least what we'll start to use in our own model for how we know what our actual prediction is here. So actually I meant to keep that. We'll use the probabilities, except then what we can do is it's just if it's bigger than 0.5. Because if we think that that's really what we mean, is that we would predict the class that, and I will say prediction. So this is actually Scikit-Learn. I'm going to put, sorry, 1 second, Scikit-Learn prediction and Scikit-Learn probability. So here, if we say it's bigger than 0.5, the probability, it's basically saying, okay, what's the probability that they have heart disease? Well, if I have a 50% guess, that means I really don't know. Like if I'm the model, I really don't know which one it is. But if I output, say, a 60% chance, I'd say, okay, I'm only 60% confident they have heart disease, but what really would I actually guess if you were to ask me? I'd say, yeah, I mean, it's more likely that they do have heart disease than they don't, because I give it a 60% chance, and vice versa. If it was a 40% chance, I'd say, well, I'm not super confident, but I predict that they don't have heart disease. So that's really what this does here, and that's all that the predict function itself in Scikit-Learn is doing. It's just asking if it's bigger than 0.5. And so here's our column here. This is outputs to false. I actually would rather convert that to int, so we're just going to wrap that in an int. Actually, it's going to be a NumPy array, so I might want, that probably won't work. We will actually do dot as type numpy dot int, and we haven't imported numpy yet, so I'm just going to do int, and I think that would work just fine. There you go. Okay, so we can see it's not matching in many places to the actual, which is kind of iffy because we wanted our predictions to be pretty close. So let's we graphed the data here. Now what we can do is graph our probabilities on this, because we have in each data point here, we have an associated predicted probability. And so let's take a look at the logistic regression curve. So Plotly can make some really nice graphs. It also, the syntax is fine, although it can be a little bit much. So don't worry too much if you get annoyed with the syntax of the graphing. It's just kind of, it's something I always get annoyed with, but you just have to look up what to do and you'll figure it out. So import plotly.graph objects as geo. That's not what I said, and Colab can really annoy me sometimes because that's not what I wrote. So just do what I wrote. Thank you. Import plotly.graph objects as go. Fig is equal to go.figure. Okay, so we're making a more complex graph. That's why we can't use the plotly express library. We have to use the main graph objects library. We can add a trace, which is basically just adding some sort of function plot to it. We can add trace geo.scatter. X is equal to predictions df sub the max heart rate, and we'll set y is equal to predictions df sub heart disease. Okay, and then there's a little bit more we have to do for this same graph here. We're also going to add in that the mode is equal to markers. That is how we actually plot these as points and not as lines. We're going to want them as points. Mode is equal to markers, and we'll give it a name for the legend, so that is the name is basically the observed values, because the other one is going to be for the predictions. This is the actuals, so name is observed. And marker is equal to, this is just an artifact of the graphing library. It's a little bit annoying. We can do marker is equal to the dictionary of set color to be blue in strings. It'll know to convert that to blue. And if I output this, it's also just fig.show like it is with matplotlib. And that's our graph, which looks exactly the same as before, but the colors are a little bit boring. Okay, and that's totally fine. We are now going to add a piece to this graph, which is our predictions. So we can do fig, and actually I'll just really copy this because it's going to be slight changes from that. Fig.addTrace a go.scatter. With the predictions df, the max heart rate is actually still fine. And the predictions df, we're going to add in the probability. Okay, and so we called that the Scikit-Learn probability. So here it is, Scikit-Learn probability. We'll set mode to be markers, name is observed, and marker to be color of anything but blue. Let's go with green is a nice curve. And if we do fig.show on that, there it is. Isn't this beautiful? No, it's not, because this is not called model predictions or model probabilities, basically. So here we have all the data, and then with these same associated x values, so we see here they're always going to be lined up because it's the same x's. Here's what our model predicted as the probability that they have heart disease. So all of these people, we think it's very likely they have heart disease. Then it goes down in this weird kind of curvy fashion. We'll see what the actual function of this looks like. And so it curves down like this. And then basically here is where, at this point, at 143, we can see this is where our model started deciding that these predictions should be labeled or guessed as not having heart disease. So all of these guys, it would label all of them as predicted to have heart disease. But then at 0.5, it would say, no, I think it's more likely they don't have heart disease at this point. And these are all the probabilities associated with it. Okay, so pretty cool stuff. I really, really like it. And we are going to add, just to make this graph a little bit prettier, and we'll keep this pretty much the same throughout all the graphs that we're going to make. I'm just going to add this extra piece here. Update the layout, set the title, heart disease versus max heart rate and heart disease, just to give you his title and some labels there to make it better. I want to do one more graph before we move on, and that's going to be basically the exact same thing. So I'm going to copy this, except I want to actually plot the predictions as well on here, the predicted classes, either 0 or 1. Here's the observed values, here's our model probabilities. I'm going to show the exact same curve, except instead of the observed values, I want to say, I'll change this to be basically the model probabilities, which still, it was the model probabilities before. I'm just labeling it more explicitly as that, so that this is model predictions, the output, and it is going to be predictions sub Scikit-Learn predictions. I think that's what we called it. I guess we did not. Did I call it Scikit-Learn prediction? Yes, I did. Okay, so Scikit-Learn prediction, color blue and green again is fine. So now we can see here is a very hard cutoff where it's like right here. This is where we stopped predicting these to be. Oh, sorry, never mind. I thought I did something wrong. These are all the predictions for the heart disease class. These are all the non-heart disease. And here at the 50% mark, we can see it's like, nope, I'm going to start changing to these ones. So hopefully that made sense. This gives a really good foundation for when we implement it from scratch. And now, what do we do to actually measure the error in our model? You can see it's obviously not going to be right in many places. Here, you can see like it's wrong, you know, like in so many places here. Sometimes it's right, sometimes it's wrong, sometimes it's right, sometimes it's wrong. So what we can measure is the idea of accuracy, which simply means you know, did the model get it right? We'll give it a check. If the model got it wrong, we'll give it an X. We will basically sum all of the ones that we got right, divide that by the total number so that we have some fraction that outputs a percentage of how well we did. That's formally what accuracy is. It's a percentage of correctness. And so we can get that quickly from Scikit-Learn dot metrics import the accuracy score, and we will output the accuracy score of predictions df sub our Scikit-Learn prediction, and we'll compare that to the actual. No, apparently I won't. Scikit-Learn prediction. I got a key error again. Predictions df sub Scikit-Learn prediction. How could that possibly give a key error? What are we doing here? Scikit-Learn prediction. It was totally fine with that. There's no space at the end. There's a, gosh, sorry about this, having a rough go. Scikit-Learn prediction, Y-train, there you go, 67% accuracy. So what does that actually mean? You know, like how good is that? I mean, it's okay, 67%, but there's definitely a lot to be improved upon. But it's pretty great that you can actually get, you know, 50% is our guess. You know, that's basically the baseline model is just a coin flip because there's only two classes. And so 67% is obviously a lot better than 50%. So we're not too upset with that. Now let's dig into the model just a little bit, and we can output these things called the intercept and the coefficient. So lr.intercept underscore and lr.coef underscore. These are our two parameters, and I hope that hopefully you did watch one of the two previous videos, but if you haven't, basically, you know, these models are about learning parameters. We're learning numbers that try to minimize the error. So this one, what it got, Scikit-Learn optimized this and got what we'll call alpha hat. The intercept is alpha hat equal to 5.33, and the we'll call beta hat negative 0.037. It liked those parameters. That's the curve it fit. It could have actually done one where it kind of looked the same, but it moved over side to side. So you can think about a translation. That's essentially alpha hat's interpretation. So if we increased alpha hat, it'd basically be the same thing but shifted over. And if we you know, increased this value here, the beta hat value, then that would kind of produce a sharper slope going down. And since it's negative, that's important. It's negative, which means we think that it should be shaped down like this, where as you increase this X value, as you increase the max heart rate, that the probability of heart disease should go down. But this could have been a positive curve. We could have got a positive coefficient here, positive slope, which essentially means it would be curved up like this. As we increase the max heart rate, the probability of heart disease would increase. But that's not what we got. We could tell that wasn't what it should have been from the data at the beginning as well. Okay, so that's pretty much what we've got for implementing it in Scikit-Learn. This is how you would kind of do this idea. You know, we would still get more complicated than that. And if you want to stop here, please check out my video about making train test and validation sets, because that would be very helpful as a next step. But to carry on with the idea of implementing from scratch, at least actually pretty much just start with the idea of implementing from scratch, because that's not what we did first. We'll go back to heart and get heart.head. Okay, so I have a little bit of explaining to do, but don't worry, we're going to take it nice and simple. So I'm going to paste this in. We're assuming that the probability of the heart disease of the ith person, so the first, the third, the fifth person, whatever, their probability of heart disease is equal to alpha, which is some number, plus beta, which is some number, times the max heart rate of that ith person, plus some error. Now, can anyone tell me what's wrong with this? Put your hand up. This isn't live. I'm not listening. So basically what the problem with this is that this is the formula for a line here. Okay, this is going to draw either an increasing or decreasing line. For us, it would actually be decreasing most likely, but it doesn't matter. And this produces values between negative infinity and infinity. It's going to go all the way and produce this line. But we want probabilities. We want the probability of there being a heart disease, and it's kind of tough to do that when you have like a value that's like 4. If this output's like 4, I don't know what the probability is. We want a function that actually takes basically any point from negative infinity to infinity and translates that into a probability. Okay, so we need some function that maps real values or continuous values to the range of 0 and 1. And it turns out there's this function. It's also called the logistic function, and that's why it's called this. But I'm going to call it the sigmoid function. Okay, it's some function which does something, and we'll look at exactly what it does. If we wrap this, then what this does, and there is technically error as well, as the probability is a little bit off, but there's a little bit of a mathematical problem with saying that this is accurate. But essentially this is the idea, where this produces a value between 0 and 1. It's the probability, and we're off by a little bit. We're not quite completely correct, because there's going to be some error in there as well. Now, something else I'm going to paste in is more generally, this is for max heart rate in heart disease, but more generally, it's that the probability of yi, or output, is alpha plus beta times xi plus the error. Again, we need to wrap this in the sigmoid function for that to make sense, because that outputs between 0 and 1. And I wrote this more generally because, we want to abstract this into a more general idea. And so our model itself is the exact same thing, except only this piece, and we're going to replace the alpha and beta with hat. And the reason for that is really just mean estimate. Okay, we're just trying to estimate alpha hat and beta hat, trying to find the best ones that fit the given problem. And so that was Scikit-Learn. This was alpha hat and beta hat. You see how many decimals there are here. That's probably not the true alpha or beta, but it's a really good guess of what it is. Okay, so that's the model. And this is, that's the setup basically. So I'm going to copy in here some function which we want to build, which is called getProbabilities. GetProbabilities, model in X. It obtains the predictions for the given model and the inputs, okay? So the model is going to be a dictionary where we feed in alpha hat, its number, and beta hat is a number as well. And X is going to be a NumPy array of floats with a shape of n, where n is the number of examples that we have representing the inputs. And it's going to return a NumPy array of floats with the same shape. So it's going to be 1 to 1, basically mapping these inputs to predicted outputs, representing probabilities. And so each of these values have to be floats between the range of 0 and 1. And we're going to be using this softmax, this is actually a simpler version of the softmax function, which we might see later. We'll definitely see that later, but not this lecture, okay? So we're going to be using that sigmoid function. Now, what the heck is that sigmoid function? So let's actually leave this for now and take a step back. Actually, I want to do one thing first, which is the linear regression formula. It's actually the logistic regression formula is exactly the linear regression formula. So this is that formula, or also this is that formula. And then you just wrap it in the sigmoid function. So what we can do is alpha hat is equal to the model. We'll grab the alpha hat, we'll get that out, and then we'll get the beta hat is equal to the model sub the beta hat. And then we will return the sigmoid, which we haven't created yet, but don't worry, we will make that function. Return the sigmoid of alpha hat plus beta hat times the input. Okay, so this input is going to be a vector, a big long list of inputs. We can multiply all of those by beta hat, and then you can add alpha hat to all of those. That's basically your linear regression formula. And then we need to wrap that in sigmoid function to make that between the range of 0 and 1 to be probabilities. So let's make that sigmoid function. It turns out, I'm just going to tell you, define sigmoid of x. What we can do is return, and actually I'm going to need to import numpy for this. Import numpy as np is how you do this. We'll return 1 over 1 plus the numpy dot exponential. So E is essentially just a constant that's very close to 2.71. So if this concept confuses you, or you're writing the code along with me, just change it to 2.71 if you want to. It'll be pretty much the same thing. But that's not quite true. Actually, don't do that, because numpy.exponential, this will make this work with numpy functions, okay? So numpy.exponential of negative x. Okay, so we do sigmoid of x is actually 1 over 1 plus e to the negative x. And you might even see it written as, I believe the equivalent way is e to the x over 1 plus e to the x, I believe. And yeah, that's right. So yeah, that's the sigmoid function. That's all it does. And so we can actually ask a range of this thing. And actually, I'll just show you an interesting fact, and that's kind of why this works out so well. Sigmoid of 0 happens to be 0.5. And let's take a look at the graph more closely. So if we get, we'll just say a test range is equal to numpy.arange. We haven't seen this function before, but really it's just making a numpy array in the range -50 to 50. And we will get a figure. Fig is equal to go.figure. And okay, not sure why I deleted that. That's not what I said to do. Go.figure. And then we'll add a trace, fig.add trace of a go.scatter, setting the x equal to the test range, and the y is equal to the sigmoid, y equals the sigmoid of that input there. So y equals sigmoid of the test range. Okay, and so again, what this is going to do, this sigmoid, it's okay with a numpy array, and so it'll take in this whole vector, this whole input, this whole range here, and it'll apply the sigmoid function to all of these. So this whole thing is the sigmoid. It's going to be x as this range, and the y is the sigmoid of that location. And then here we can see as our graph, that is the sigmoid function. Okay, so here 0 is right at 0.5, and then here, so around the -5, -4 values, it starts to really rapidly increase, and then it goes and stops increasing a lot at around 7 or 8 or so, and it kind of flatlines to, it's saying 1, this is not 1, it's very, very close to 1, and so it's bothering to say that, very, very close to 0, but it never gets below 0, and it never gets above 1. It's always between 0 and 1. Okay, so we're going to be using this function. Well, actually, technically, we're already using this function because this sigmoid function works now, and that's what we called it. So that's what we do. We wrap sigmoid around alpha hat plus beta hat times x. That is exactly what our model is. So we can test this very easily with, we'll just say, make a test model is equal to, it's a dictionary. I'm going to show you another way of making a dictionary just for fun. We can do alpha hat is equal to 2, and beta hat is equal to, let's try -0.01. I actually did a little bit of cheating this beforehand and looked just to make the tutorial look a little better. I picked those values on purpose, but it doesn't matter. Predictions, df sub, we'll say our model probability, and actually I'll do spaces here, our model heart disease probabilities. Okay, and they're not really, this is our test model, so this probably isn't very good, but let's see what it is for now, and we'll update that later. We'll set that equal to the get probabilities of, we'll give it our test model, and you're about to not be able to see what I'm doing. So let me just delete myself for a brief moment here. Test model, as well as we can give that, sorry, I got lost after I got rid of myself. Test model, and our inputs is going to be, that'll be predictions df sub the max heart rate. And that's going to be in a NumPy array actually. So before we had, I think it was xtrain. So xtrain is, it has the shape. This is the max heart rate. So xtrain.shape, it was actually 918 by 1. If we flatten this thing, we can actually do xtrain.flatten, and that removes that extra dimension we don't really want. But we can ask its shape is it's right there, 918 comma. Okay, so I'm going to replace this with just xtrain.flatten, which is just the max heart rate here. Okay, so all I'm giving it here is asking the probabilities for given the test model, which for some reason I capitalized that. Glad I noticed that, and then giving it the inputs that it's using to actually predict with the max heart rate. Okay, so we can do that, and then predictions df, we'll output that. Here is our last column here, our model, heart disease probabilities. You can see it's way off from Scikit-Learn's. It's not good at all. We are not a fan of that. Okay, but we will plot it anyway. So let's make a graph where we can see a bunch of different things. I want to see the observed values. So that'll be the ones and the zeros. I want to see the Scikit-Learn graph. I want to see our graph, and we're also going, or our probabilities, and I'm also going to plot the threshold, which is basically just the 50% as a horizontal line, as a constant. Okay, so this is going to be a bit of a lengthy graph here, although a lot of it probably could be copied and pasted. That's what I did before, but I want to type this out with you. Not sure if you heard that honking, but that was a very loud honk. Fig is equal to go.figure. We will add a trace, fig.addTrace, where we do, first we're going to do the observed. So that's the actual values. Go.scatter with x equals the predictions df. X is the predictions df sub the max heart rate. And y is equal to the predictions df sub heart disease. We will set the mode. Well, where is that? That's probably not right. We'll set the mode. Oh, I didn't bring myself back again, did I? I'm disappearing. Actually, that's fine for this. This might get a little bit lengthy. So we'll set mode equal to be markers. We'll set the name. Why does it look like that? That's not quite right. Mode is equal to markers. We'll set name is equal to the observed value, so what actually happened, whether they did have heart disease or not. Observed, and marker is going to be set equal to the dictionary. And I'll write it like this again, dict, where the color is equal to orange. Okay, and just to show you that this works, and I'm also going to grab that same update layout as before. Fig.update layout, fig.show. In dot syntax, I probably just missed a bracket if I had to guess. And there you go. Okay, so that's in orange. That is our observed actual values there. And I'm surprised it's not giving a legend, even though I gave the name. It'll probably start getting that soon. So now I'll ramp this up a little bit quicker. The Scikit-Learn probabilities from before is going to be the same thing, except, so I'll copy that in. The Scikit-Learn probabilities, that's predictions df max hr. This is sklearn probabilities, I think is how I wrote that. Let me just check. Color is, I'll make that blue, and name is equal to sklearn probabilities. And it's got a key error, so of course I'm getting that label wrong. That is sklearn probability. Why was that wrong? A capital L, I'm guessing. No, oh, lowercase. It was lowercase. Didn't I make it? I swear I was wrong with uppercase earlier. Whatever. Sklearn probability. Sorry about that. That is the Scikit-Learn curve right there. There's our legend. We can now do another plot, which is this one is going to be for our new predictions. Okay, so what we just did here, our model heart disease probabilities, that model we just did, and we'll do sklearn, not sklearn probability. We're just going to copy that name in right there. Our model heart disease probabilities. It's a big long one. Right there. And I'll just add that in as well. We're going to make the color equal to, say, red. And I'm going to show that. Hopefully that worked fine. There you go. So our model heart disease probabilities, there's that curve right there. It even almost looks like a line. It doesn't look great. There's sklearn probabilities. And just for fun, I want to show you a threshold value. And what this is, and I'm just going to copy this in because I think this will work as is. So fig.add trace go scatter, where x is the predictions df max hr. It doesn't actually really matter, the x here. The y is just 0.5 over and over again. So it's only going to be 0.5, the length, just to match this length. And then we'll call this the threshold, which is basically the value where, 0.5. If it's higher than 0.5, then we predict that you do have heart disease, and less than 0.5, less than the threshold, I guess purple. I don't know. Let's go with purple. And I'll just bring myself back here, and we can see here. So it is at this point where sklearn decides to stop saying that we should stop predicting that they have heart disease right here at 143, where the max heart rate is at 143. But it's for our model, it decides way over here. It says, actually, let's wait until it's like 195 to do that. That's going to create a lot of error. And we can confirm that with, if we look at the accuracy score of, we'll just get predictions, df sub, that is our model heart disease probabilities. And we compare that, actually not the probabilities, but whether that is greater than 0.5, remember from earlier, this is how to convert that to actual predictions. And we'll just wrap, I think that is probably fine as is actually. And then we'll just give that y train is actually going to be fine as well. So here, this is only a 55% accuracy. It's only really slightly better than a random guess. We don't like this curve at all. It's not quite good. And so we'll change, we'll try changing manually for a second, and we'll try to optimize these values soon. Let's try just setting beta hat equal to negative 0.02. And the probabilities, they look a lot closer. It still looks pretty far off. But it looks a little bit better. And we'll run this again. And here's our red curve. Okay, at least this looks like a somewhat reasonable curve, even though it's not. It's really not very good at all. We can see the accuracy goes from 55%. Never mind, that's even worse, 49%. If I set the alpha hat, maybe I have to increase alpha hat just a little bit. It's funny. I thought that I was keeping values from earlier that I checked, but clearly, that was not any better at all. I'll change that a little bit and get our curve. Oh, that's a crazy curve. I do not like this at all. And that's 55% again. Okay, so that's basically because we're just predicting all of them as the positive class, the heart disease class. And it looks like a little bit more of the data actually has heart disease. And so if we predict that every time, then we actually get 55% because there's 55% of the data that actually does have heart disease and 45% that doesn't. Okay, so clearly, I can't solve this myself. Like, I'm having trouble finding the values that make the right curve here. And so we want to actually optimize this and find, basically try to minimize the error here, just like sklearn or Scikit-Learn is trying to do. Now, it's a little bit tricky. So with linear regression, I spit this formula in your face twice. With simple linear regression, I gave you kind of a simple formula. Simple, it's still pretty complicated. Formula to minimize the sum of the squared errors, or the mean squared error function. And so that, that worked for linear regression, and that was fine. But for logistic regression, we don't really have that same luxury. In fact, it doesn't really exist what we refer to as an analytical or closed form solution. It means a formula for solving to basically get this curve like this. There's a bunch of different methods that you can use, and there's ways to minimize pretty much any error function. And we're going to do that without even really knowing what we're doing. And if you want to take a look at the idea of gradient descent, you can take a look at that in my ML course, which is incomplete, by the way, but that part is mostly complete. And that would give some insights for that. But that isn't even necessarily what we're going to be using to optimize. That's just some algorithm. The point is that there is some algorithm out there that we can use to try and get a curve like this, to try and minimize the error. And in particular, we're still going to actually minimize the mean squared error, which means here we have error here. This is actually 1, but we predicted like 0.97. Here we have a ton of error. We predicted 0.94, but it was 1. And here, you know, this value here, we have a ton of error because we predicted 72%, but it was actually 0%. So that's off. There's an error of 0.72 there, and we'll minimize where we take the errors. So this is one error, 0.72. We'll actually square that and then sum that with all of the other squared errors or distances as well, to get some positive value, positive error, where it's positive because we're squaring distances, and squaring is always going to be positive. We're summing squared things, so that'll be positive. That gives us some squared error that we can try to minimize. Now, it's a little bit weird to try and set this up in Python, I'm going to be honest. And this is actually the first time I did this, because this is not really something you do normally. But it is a useful skill, clearly. And if you want to know how to do it, then this is how to do it. So we're going to use from SciPy, which like one of the first time I've actually used SciPy, from SciPy.optimize, we'll import this minimize function. And we're going to create this bad boy right here, this function, which is define getBestModel, which returns the model with the parameters that best minimize the mean squared error, and x is the NumPy array of floats with a shape of n, of inputs. Y is a NumPy array of floats with shape n, of outputs. These values, which actually, you know, they're floats, but they might be floats. Really, it's floats between. It's literally. Actually, I'd really rather say they're ints, even if they're actually casted as floats technically. They're really int values in the range, and this e is as close as I can get to is in. I'll just do int in 0 and 1, because these outputs are actually always either 0, which is that they, or I don't know if I said inputs or outputs there. These outputs are actually either 0, which is they do not have heart disease, or 1, that they do have heart disease. So the x here that I'm pointing to a screen you can't see. The 168 is the x's. These are all the x's, that first value in the tuple, and the y's, those are those. That second value in the tuple is the y's. So if we're given those things, we can return alpha hat as a float, the best alpha hat or best intercept that minimize the MSE, and beta hat, the best one that minimize the MSE. Basically, we're just trying to find these two values that produce this curve. We're trying to make this curve, and we'll do that with SciPy. Now, I'm going to write something that's not really going to make sense quite yet, because we haven't done the other part. What we want to do is get this result thing, and the syntax is a little bit weird. It confused me too. We'll do res for result, is equal to the minimize. That's that thing we imported. We'll minimize the function to minimize. That doesn't exist yet, but we're passing this function to minimize. We'll make that x0. This is the idea of starting values. So it doesn't matter too much, but basically we're going to start with some guesses of alpha hat and beta hat. And so we'll just set them to 0 to start. And that produces an interesting curve. I'll show that curve for you, which is if I start them at 0 and 0, we can see it's very clearly wrong because it produces all of them equal to 0.5. And so that's actually our model right there. It's the same as the threshold. It's kind of cool how it highlighted there. And we don't want that curve. Okay, so in that accuracy, 44%, it's not great. So the starting values, we'll start them at 0, but don't worry, it'll optimize that and get them down later. We'll pass these args, which is essentially it's a little bit of a weird concept, so don't worry too much, but we're gonna pass in the x and the y as well, and we'll kind of see where that ends up. Now, we're gonna get parameters back which is equal to result.x. I know it's weird, it's .x. This is just a tuple of the parameters. The first part will be alpha hat, so we can get alpha hat as the first one and beta hat as the second one. These are the best alpha hat and the best beta hat is equal to parameters sub 0 and parameters sub 1. And then the best model, we're calling it best because that is actually optimized at this point. Best model is the dict is equal to the dict of alpha hat is equal to alpha hat and beta hat is equal to beta hat, making it that dictionary model, and then we'll just return the best model. Okay, so this is kind of weird. Basically, we're calling this minimize thing. We're minimizing this function. We're passing starting values for alpha hat and beta hat. And we also need to send off to this weird thing the arguments, which is the inputs and the outputs. And we'll see why shortly. We can get the parameters back, and then we'll just return the best model. So, well, we'll make above this now because we're assuming that this thing called function to minimize exists, but it doesn't right now. Function to minimize is, and I'm not going to write a nice comment for it because it's just a weird idea. It's going to be doing, we're going to need from Scikit-Learn.metrics, the mean squared error, because we're trying to minimize the mean squared error. But I can't just say minimize the mean squared error. I have to do this kind of more complicated idea, which we'll see here. We can do define function to minimize. Here's our function. And it's going to take these two things called params and star args. Just bear with me, trust me. Set alpha hat equal to param sub 0, like before. So this is basically before. Here, we are extracting back the best ones. Here, this thing is going to be called a bunch of times, and it's basically just iterating over, trying different values of alpha hat and beta hat until we get the ones that we want. And so here, we get alpha hat is param sub 0, beta hat is equal to params sub 1. And then the model so far, basically, the model so far is equal to whatever alpha hat is right now. And I know it's weird I'm saying right now. I really mean when we're in this loop that you won't see, but we're in a loop of just constantly trying alpha hat and beta hat, trying alpha hat and beta hat, trying alpha hat and beta hat, and trying to minimize the error iteratively or over and over again. And so what I mean right now is whatever it happens to be at this point, alpha hat, not at this point, but in the loop. Alpha hat is alpha hat, and I'll set beta hat. I realize I switch between these dictionary syntaxes a lot, which is probably kind of confusing, but at least we're used to both. They do the same thing. Alpha hat, now alpha hat, beta hat, and we'll set x is equal to the args sub 0, and y is equal to the args sub 0. Okay, so at least you can probably appreciate that we sent args off as this tuple of x, y, and we're extracting out here as x is args 0. Sorry, you won't appreciate it because I wrote that. X is args 0 and y is args 1. This is our inputs, this is our outputs. So we can get the probabilities that we have so far. So again, in this loop, we can get prediction probabilities is equal to that get probabilities before of whatever our model happens to be at this part in the loop, and then we can also pass it the input. Okay, so this is our predictions for whatever alpha hat and beta hat happen to be. Those are our probabilities, and then we can just return the mean squared error of the prediction probs and the y. Okay, so this is the function to minimize. The function that we're trying to minimize is the mean squared error of our prediction probabilities and our outputs. That's what I described before, remember? I was saying for our curve, we're trying to do the mean squared error of whatever our model parameters are, and then the difference between the observed, this is y, the x is going to produce the prediction for y, and we'll get the mean squared error. So that's the function that we're trying to minimize. This is this weird process on how we actually can send it over. Maybe there's a better idea. Maybe there's better code for that, but that will definitely work, and I hope it makes sense. Okay, so we'll try that. And how do we test this thing? Okay, so we'll get best model by calling get best model, that function we just made. No, not that. Get best model. And do I exist right now? Yes, I do exist right now. Okay, I wasn't sure if I did. Get best model on, we'll pass in predictions, df. Actually, no, that's not quite necessary. We can do train xtrain dot flatten. That's our input. And we can do predictions, df prediction. Actually, should it be flattened? So I'm trying to think right now because it wants yes, it wants n comma. So flattened is correct. We want predictions, df sub. What are our outputs? That is sub heart disease. Or also Y-train would probably work there as well. If you see me interchanging between those, and I know I am, it's because multiple things often work. So, and then best model. What's the best model? Alpha hat is 5.51 and beta hat is negative 0.038. Okay, so negative 0.038. What was our other model? Our Scikit-Learn model was really close to that. We got 5.5 and negative 0.038. They got 5.33 and negative 0.037. Okay, which one's really better? Probably Scikit-Learn's, although I bet ours is pretty darn good as well. Okay, so we just got the best parameters, and now we're able to produce a curve that's, you know, pretty close to this one. So we're just going to do the kind of irritating code that gets that done. Okay. So actually, it probably isn't irritating code at all. It's probably as simple as just updating, copying and pasting this code. So it should be right here. Except right now, the one that's our model heart disease probabilities, is getting past these probabilities right here. Except we can just override that variable. We can just set predictions. Actually, I can just copy that. Did it just crash? No. Predictions df sub our model heart disease probabilities is equal to the get probabilities on, what is it? The get, well, we already have the best model. Best model's right there. So we can pass it in the best model with x, and we'll just do that xtrain.flatten should work there. Okay, so if we override that and we set predictions, did I forget the p? Not that I forget to p, I did that. Predictions df is overrided with our model heart disease probabilities. Looks very, very close to the Scikit-Learn ones. Okay, so if we run this again, we should see, there you go. These curves are basically on top of each other. The Scikit-Learn probabilities in blue, our model heart disease probabilities in red. We just implemented logistic regression from scratch and we plotted it beautifully. How awesome is that? It really is great. Let's look at the error of our model just to make sure. It's probably very, very similar. I'm just gonna, wherever I grab some accuracy here. It actually should, this is just a complete copy paste. Actually, yeah, we'll copy and paste it, but I could have just ran it right there if I really wanted to. Here, our model heart disease probabilities greater than 0.5. That's how we produce our actual predicted classes. We'll compare that accuracy with the observed, and we can see it's 67% like it was in Scikit-Learns. Okay, so that's really, really awesome, and we could be done. Although, if you recall, with this is what we did. This is basically called simple logistic regression because we used one input variable, and so we can graph it like this and make this curve. But with multiple linear regression, as we saw, we had multiple variables to try and predict our continuous output. We basically said alpha hat is beta 1 hat times x1 plus beta 2 hat times x2, and so on for whatever we wanted to do. We can do the exact same idea, exactly the same. If I go back to this comment right here, where is it? So much code. Right here, where we said alpha and beta, I could just extend this idea to, instead of, and I'll just pick this one. Instead of alpha hat plus beta hat times xi, it would be alpha hat plus beta 1 hat times x1 plus beta 2 hat times x2. All that way, keep that inside the sigmoid function, activate sigmoid after, and that might produce a better model if we have more variables. So I do not want to go through the hassle of updating our getting best model and this function to minimize so that we could do that. If it's a great exercise if you want to be able to try and adapt this to work with multiple logistic regression as well, or basically what we would just call just logistic regression. I'm not going to implement that for you, and it's not too complicated, but it'd be a little bit irritating on the code, and it's just a long video already, so I don't want to do that. Go ahead if you want to. But I will show you how to do it in Scikit-Learn very easily. It's extremely easy. We can just do, I'll grab some variables here, and actually I'll just copy some code here to be quick. We can get train as a data frame is, we can grab age, the resting BP. Actually, I'll show heart for you very quickly. So that's our data frame. We can grab many variables here, and actually I still haven't showed you how to use the idea of categorical variables as inputs, like the gender being a binary variable. Haven't looked at that quite yet. I'll probably do that in the next video if I can. Right now I'll stick with the continuous values of age, the resting BP, the cholesterol, and so on. They probably have each of their own beta patterns. Those slopes, either negative, I drew positive, but sorry, I'm making this more complicated than I need to. Basically, each of these have some associated beta, which is either negative or positive, to help try and predict the class. So we can have train as these things, and X train and Y train is we can grab train as all of the rows and then up until -1. That's a NumPy array, so I can man, stumbling on words at the end here. Sorry about that. That's our input matrix, and this is our output vector, which is that heart disease column at the end there. And our shapes are these things, and we would make a logistic regression model and predict the accuracy or guess the accuracy like this. We grab a logistic regression model, we pass it X train and Y train. Here, this is no longer 1, this is 4. And we can do our prediction and get our accuracy to get it up to 70% rather than 67%, which is probably a little bit better, okay? So I hope that was great. A really good lesson implementing this idea of logistic regression from not too mathy a point of view. Really good practice on Python, NumPy, and Pandas. A little bit of mathy ideas just to get your brain kind of flowing in that direction. And it's really important to be able to implement these ideas without like a ton of effort. Just at least knowing that you're able to do this and going through the practice is really helpful. And obviously it helps you understand the idea itself so that we are able to do this. This is what you would then kind of do in practice. But you know, there's so much more to understand under the hood rather than just kind of learning this right away and not doing anything with it. I think it's worth it. So thanks so much for watching this video. If you did get this far, you are killing it. That's really great. It was a long video, very helpful one. And yeah, the next one we are going to, I don't know. There's some exciting ideas coming up and I'm not going to spoil it. So you better subscribe. I assume you're subscribed if you got all the way to this point. If you're not, you got to do that. It's just a good idea. Okay, so thank you so much, and I'll see you in the next one.